Hello and welcome to Spaced Out. I'm your host Sarah Begum, and today we have a climate special episode. Our climate is experiencing rapid change on an exponential level since the last ice age 10,000 years ago. By the end of this century, the average temperature will rise from 1.5 degrees to 5 degrees Celsius. There are 4 EU Copernicus Sentinel missions and 4 Earth Explorer missions observing Earth from space to provide scientists and key decision makers in government with accurate data about climate change, the effects of climate change, and how the world is changing, so that they may respond accordingly. The mission's focus include matters such as deforestation, retreating coastlines, sea level, all the way to ice thickness and more. Joining me today to discuss Space for Climate is Head of Climate Office Suzanne Mecklenberg from the European Space Agency's Earth Observation Department, and Sophie Hebden, Research Coordinator from Future Earth Network and ESA's Climate Office. Welcome to the show.
Thank you.
Satellites are the only way to gather data on essential climate variables, and to respond to the need for climate quality satellite data, ESA set up the Climate Change Initiative. What are these essential climate variables and how are they gathered from satellites? And how is ESA's CCI responding to the data to manage climate change on Earth?
The Climate Change Initiative tries to quantify essential climate variables. Now, what are essential climate variables? It's a group of 54 parameters that have been defined by the great and the good in the climate networks. So essential climate variables are essentially indicators of how our climate is changing. So we would measure, for example, how high the sea level is in the oceans. We would measure what the temperature in the oceans is. We would measure the salinity, which is important to understand currents, for example, in the oceans and how they change. We would measure things like biomass, which is telling us how much vegetation we have on the planet, which could be an effective CO2 absorption sink, let's say. And there's many more of them. And we've been addressing roughly more than 20 of them. And we're also looking into how we can combine these different climate data records in bigger projects where we talk about, so for example, a sea level budget. So where do all the different effects of sea level rise are actually coming from? So it's quite a large program. We're using predominantly satellites from ESA, but also if there's no other measurements available from our own satellites, we are using data from other providers' satellites. So, for example, from NASA, the American Space Agency, or from JAXA, the Japanese one, or any other sort of private provider that we can actually get some data from that are important for us. And at the moment, we have, as you said, 4 different Sentinel missions in space. Out of a fleet of 6 that are planned. We have, since quite almost 10 years now, a Sentinel-1 is in space, which is a SAR mission, a synthetic aperture radar mission, which gives us characteristics of the surface of the Earth. We can also use these data, for example, to look at currents in the ocean. Sentinel-2, which is more an optical mission, so we look at things like land use or the status of vegetation, for example. Then Sentinel-3, which was my mission once upon a time, is very special in the sense that it has actually 3 different instruments on board that measure the height of the ocean, that measure, for example, vegetation indices, and that measures land surface temperatures. And then just recently we launched actually the 6th Sentinel, but the 4th to be launched. It is Sentinel-6, Michael Freilich, named after a NASA administrator who was very instrumental in Earth observation, who died unfortunately last year. It's an Altimeter mission. It's a sort of reference mission to many of these Altimeter missions that are already in space and help us understand how the height of the oceans, for example, is changing. And then, as you said, we also have Earth Explorer missions that we're using now. Some of them we are using in the Climate Change Initiative, others not necessarily because they're not relevant for our measurements that we need to calculate these essential climate variables. So the two big ones that we're probably using at the moment are Cryosat and SMOS, both of which have been in space for over 10 years. And that's important to know because these measurements, especially from the Earth Explorer missions in ESA, they're very new. They're one of a kind. They're usually a demonstrator type of data set, which basically means that we don't have maybe similar sensors having measured what they measured before. But for climate, it's important to have long-term data sets. Data sets of a year or two might help you to understand maybe some processes in the bigger picture of climate, but it will not give you a long-term series. So we've only recently started to use these data from Cryosat and SMOS because they are now, about a decade in space, and that's an important point to make actually in terms of how we can use satellite data.
That's really interesting. What is unique about this specific satellite that you're not that isn't available with the others?
So, for example, if I can talk about SMOS simply because I was the mission manager for SMOS, so I understand it probably best. SMOS measures two things. It measures the amount of water in the soil or the amount of salinity in the oceans. Particularly the salinity part is something that we are at the moment using in one of our essential climate variables quantifications. So we are basically measuring salinity. Salinity is important to understand the motion in the ocean. So basically the currents or the change of the currents, for example, because it's basically temperature and salinity that drive the currents in the ocean.
Oh, that's really good.
Until we launched SMOS in 2009, we didn't actually have measurements of salinity from space. So before then, and we still have measurements from floats, from drifters in the ocean. So that's what we call sort of ground-based in situ measurements. And we still have them because we need to validate that what we see from space is actually really there. So we're using these ground-based measurements to verify that what our satellite measures is actually true.
That's so interesting. Gosh.
So we have basically had three missions that actually measured salinity from space. The first one was SMOS from ESA, and then two more came from NASA, Aquarius and SMAP. Aquarius unfortunately only flew for 3 years, but that's also important to see because we could sort of fill certain data gaps maybe with each other's mission data, so to say, because they were on a different, not on a different orbit, but they were not flying sort of synchronous. That's what I'm trying to say. And now we have something like more than 10 years of salinity data, which already is quite an impressive long-term data series. And we also intending to extend it backwards with some other satellite data who can be a proxy for salinity. So, for example, the C-band microwave measurements. But C-band is not as, which is a different spectral band in the microwave region, it has a different sensitivity to salinity in the water. L-band is better for that one. This is why we're using it.
Global sea levels have risen about 20 centimeters since 1901, and it's been caused by melting ice sheets, glaciers, and the warming of oceans. Records show that the sea level rise is accelerating, and soon it would be lost, like deltas would be lost to the sea. More than 370 million people worldwide live less than 5 meters above sea level, and almost 100 megacities are near the water and at risk. That includes me and you. So there are 4 upcoming EO missions, including EarthCare, Biomass, Flex, and Forum. How will these EO missions benefit communities on Earth and prepare us from those living along the coastlines, near polar regions, deep and pristine forests, or people like me and you living in these megacities?
Yes, these new missions, again, 4 Earth Explorer missions, I think they're not necessarily focusing too much on sea level. I think the missions that actually focus on sea level are the altimeter missions. So, for example, the Sentinel-6 Michael Freilich, that's one of the missions that actually it continues a long line of altimeter measurements that we have since the early 90s, I think. Which basically tell us something about how the sea level is rising and what the different components are that contribute to that sea level rise, which is, as you said, the melting of the ice sheets in Greenland, in the Antarctic, but it's also things like what we call a thermal expansion. So warmer water it has a higher volume than colder water. So there's different aspects that contribute to that sea level rise, essentially, globally. But the other important thing is that it's not steady. What we have seen in over recent decades is this sea level rise is actually accelerating. So it's becoming more steep. It's becoming more rapid. Is probably the best word to say. And this is also why it's important to have all these different measurements from altimeter missions. You might wonder why we had to launch yet another altimeter mission last year, given that we have already a long series of these. But that is essentially because altimeters have a very small swath, for example. They usually something like 50 kilometers. So it takes them, for instance, Sentinel-3 has an altimeter. It takes them about 27 days to cover the same spot on Earth again. But if you really want to have a projection of how sea level is rising, and also, use it for operational applications, like, for instance, ship routing, then you need to know more frequently what the measurement of the sea level is. And that's why we have different altimeter missions that then each fill in the remaining bits of any other mission, so to say.
How many are there?
I think there's about, correct me if I'm wrong, Sophie, maybe it's 8 to 10 or something. If I'm right, there's Sentinel-3 A and B, there's Poseidon, there's Jason, there's many different missions that we have over the years. And obviously, not satellite missions, of course, don't live forever. So you need to plan ahead so that you have a continuity of measurements into the future as well.
What's the lifespan of one of these satellites?
That's very different from satellite to satellite, I would say. For instance, the Earth Explorer missions, the SMOS mission was planned for something like 3 to 5 years. That doesn't mean that it doesn't function anymore, but that's the guarantee that the producer gives you to say, I think we can guarantee that up to that point, the satellite and the platform and the instrument is working well. Nobody knows, there's different ways. You can have a failure of a technology on board. You can have a failure of the platform. You might lose control of the platform. But many of these satellites are much more resilient than we think they are and fly much longer than we thought they would. So, as I said, SMOS and CRIOSAT, they are both now for 11 years, almost 12 in orbit, which is a very long time for a satellite. Others, like the Aquarius mission that I said before, they had a failure in one of their instrumental parts, and that was the end of the mission. And then you have to essentially retire the satellite.
So what happens to a satellite once it's finished its mission? How does it come back to Earth, or what happens to it? I'm just curious to know.
Yeah, there's a new law in place since a number of years, which only applies to the ones that were started to be designed after that law, because you can't take into account. But it's basically to say you need to retire a satellite at a point when you have a particular amount of fuel left that would then help that satellite to go lower down in orbit, so it can actually enter into the Earth atmosphere within 25 years.
And then what happens to it?
And then it burns in the atmosphere.
Burns in the atmosphere. Oh, wow.
Burns in the atmosphere. So that you can do if you still have control over the satellite. But if you have a failure on board and you can't actually control the satellite anymore, then it will basically fly where it flies. and probably re-enter in a much slower way.
Oh wow, that's interesting.
This is also why we are ever more launching satellites into space, so that the space is quite full, so to say, in certain orbits, which also causes a lot of space debris. So, for example, for all these satellites that are flying at the moment, there are systems in place that monitor where other satellites are and predict their orbit. And then, 2 or 3 times a year, we would get, with MOS, for example, a warning saying, there's an object flying towards you, you need to maneuver out of this orbit so that you're not hit by the space debris. And then we would do that, and then we would move back into our normal orbit. So it's quite important to monitor this, because there can be a lot of damage to satellites if you have a collision in space.
Okay, no, you're right. We don't want space debris attacking the astronauts up there. So going back to the question, what's being done with the data gathered from these satellites to prepare humanity for the future?
The Copernicus services, which is the European Commission, and also there are plenty of other climate services around the world which provide operational sort of observations of how the climate is changing and what's happening on the planetary surface in more sort of near real time. So they kind of provide the direct policy link between the observations and government, so they can react. So there are like an emergency management service. So like, for instance, if there's, like we had last week with the glacier sort of sudden surge and the dams in the Himalayas bursting in India, they provide imagery from space so that people on the ground can respond and know where to go. So there's been lots and lots of activations of the Copernicus Emergency Management Service that other governments around the world can request help and request the images from space, and then the analysts then provide the sort of expert mapping and advice directly. And then looking further ahead, our data sets that are provided by the Climate Change Initiative are used in modelling in global climate models and decadal, sort of more numerical weather forecasting for like near time, and also decadal prediction. So the data sets from space are put into the climate model to initiate how the model sort of makes these predictions. So they're big mathematical computer models that have the physical processes of the climate inside them, and they run through hundreds of years even to predict long term how things are going to change. So I was going to say, so the observations are also used to validate the models, so they can test how their processes are working historically, to say how good their predictions are. So they compare their historic predictions with what the observations were.
So can you give me an example of how government is responding to this data?
So for instance, when there's been a big flood, the flood extent is mapped from space, and it shows where there are villages in need of aid, and so then the aid workers and the government responders can then go to those areas and provide relief.
And how long would it take?
So I think there's a delay of about 3 hours between the satellite taking the imagery and the imagery being received by a ground station and made available for processing and understanding. And then, so I think the emergency sort of management response is on the scale of hours. It's certainly not more than a day, is it, Suzanne?
Yes, I would think so too. And you can also, if there's a need for a particular overflight in a particular region, there's something called the Charter, and that's an international collaboration, let's say, between different space agency, basically providing a service. So if you say we have a flood in the north of Italy and we need some urgent imagery there, you can possibly redirect program some of our satellites, not everything, but some of our satellites we can program to basically then take images over that particular region, which will then help the emergency services on the ground to address what they actually can see there. But maybe, to come back also to your sort of more maybe long-term planning in terms of how to react to a changing climate. Under the Paris Agreement, there's different categories. So the United Nations Framework Convention for Climate Change, they came up with the Paris Agreement in 2015, which is the famous agreement that the majority of countries on this planet signed up to. It's not legally binding, but it's of course ethically important for countries to sign up and address this, because climate change is the major risk that we are currently facing on the planet. As part of this one, there's activities that go into the mitigation. So that basically means we want to limit emissions. So many countries have basically said, by 2050 we should be carbon neutral. And then countries would come up with their what they call nationally determined contributions. So it's basically the limits or the activities that they put in place to make sure that they're moving towards becoming carbon neutral. So that would mean less fossil fuel, that might mean electric cars, that might mean wind energy, different things, whatever the speciality of a country is. And that's very different from country to country, depending on their national conditions and where they are, really. And then that's one part. And the other thing is adaptation. So basically, certain things we will not be able to change anymore. So, for example, sea level rise in Amsterdam obviously is much bigger a topic than in Berlin, because it basically means that we have to put, for example, barriers in place, or we have to prevent Amsterdam from flooding. So there will be, some sort of barrier in the North Sea, something like this, and that's something that we need to. That's called adaptation, and countries do have their national adaptation plans. So they basically, in the Netherlands, obviously sea level rise will be a big topic, will not be a topic in, Switzerland, obviously. So it's different aspects that you have to address on a national level, and that's the long-term planning. Sophie was sort of explaining, the immediate effect. So, we have more extreme events like floods.
Well, focusing on these, the long-term plans, and you also mentioned the, it's a UK law as well, going carbon neutral by 2050. How has the observation of biomass and the impact of fossil fuels been observed and analysed from space over the years, and what have you learned about humanity as a result?
But biomass essentially is, maybe later Sophie can also show something in the up to that one, because it's very nicely illustrated in there, I think, as well. So basically what we do with biomass is, it's one of the essential climate variables. What it means is that we want to quantify how much vegetation is on Earth. So that could be forests, that could be savanna, that could be mangroves, something like this. And the reason why we want to know that is essentially vegetation is a CO2 sink, so it can actually absorb the CO2 that we have in the atmosphere. Mm-hmm. So if we know how much vegetation we have an indication of how much that sink can actually alleviate our emissions, essentially. So the way that we do that is that we produce, at the moment, we have a biomass project. It hasn't been running for too long. I think it's only in place now since about 2 years. They have started to produce global maps that give you an indication. It's not a snapshot. It's a sort of cumulative thing over a year. It's not on the the 7th of February 2021, but it's a cumulative assumption of what we have there, and it basically gives you the biomass. So it gives you the total amount of biomass on a global scale. And they've been produced, or the intention is to produce it for different phases, let's say, different decades, so that we can actually see what has changed. And there's different data that we're going to use. from different satellites. There is optical data, which tells us something about the momentary status of vegetation. So you would, for example, with Sentinel-2, you would see something like the onset of vegetation in spring, or the dying down of vegetation in autumn on the northern hemisphere. You use Sentinel-1 data, which is a synthetic aperture radar, which tells you something or gives you some indication also of biomass as well. And then probably the one that is most related to really measuring vegetation is what we call L-band SAR. So L-band is, again, it's a spectral region in the microwave spectrum, which has the ability to sort of monitor best, or has the best sensitivity to monitor vegetation. So, out of these different satellite products, we come up with algorithms to produce then a sort of estimate of how much biomass we have on Earth.
And what about fossil fuels? Are you able to measure that as well?
We can measure the emissions.
Can you measure the impact?
No, what we can measure is we can measure emissions. So we can measure CO2 emissions. We can measure various other greenhouse gases.
So, for example, how has COVID played a part in the reduction of CO2 emissions in our atmosphere globally since March 2020? And how can this be managed to ensure the total elimination of air pollution as we move forward?
Of course, we have seen some emissions going down simply because people haven't been moving so much. Cars, travel by air, etc., was down for a couple of months. That has certainly reduced some of the emissions about some sort of heavily populated areas. So there's this famous image over the north of Italy where you definitely see less emissions. But that's a drop in the ocean when it comes to climate. This was 3 months, and okay, we're almost a year now. But we had different ways of moving then again later in the year. We're not going to reduce with these 3 months massively our emissions globally in a context of climate.
So ESA has a mission looking at air quality for human health. How are these missions helping climate?
I think they're mixing two things here. One is sort of atmospheric composition and instant measurements that we can relate to human health. Mm-hmm. And there's a whole Copernicus service looking at that one, the Copernicus Atmospheric Monitoring Service. They have a lot of air pollution warnings on their website that they update on a regular basis, and you can go and see what that means, really. And then we are talking about greenhouse gases, which has a long-term impact on the warming of the planet, of the atmosphere in the first place, and then subsequently all the different spheres.
So recently, one of your satellites made a profound discovery on the ice sheets in Antarctica, and that was penguin poop. So can you surprise my audience with a few cool facts about why this penguin poop is significant and what it, or poop in general, can mean for the future of humanity in space?
Well, I mean, I'm not into the scientific background of penguin poop, I have to say, but what it actually highlights is that somebody we're attracting a very young audience, because I think it was designed for kids to understand what a satellite can do. And if you really think about it, obviously, it also tells you how precise and in high resolution our satellites can actually look at these areas. And I think that was the main message to interest our younger audience in some way. But in a very clever way, it sort of also focused on an area which for us in the sort of climate context is very important, because as we discussed before, sea level rise is partly because of melting ice sheets on over the Antarctic. So basically the sort of solid ice on the bedrock, but also the ice shelves around the Antarctic. It basically focused on an area that is at the moment also very important for us to look at in terms of climate change, because if these ice shelves continue to melt, we will have more of this fresh water coming into the oceans, and eventually increasing the volume of the global ocean in some way. So I think it's sort of focused on this one. I must admit I didn't really see this story in too much detail, but I think it in a clever way diverted the view.
Okay, TRUTHS, short for Traceable Radiometry Underpinning Terrestrial and Helio Studies. It's another satellite program in partnership with Airbus UK. So how will this mission help protect our Earth from future threats to our atmosphere, and why is it important?
So TRUTHS is what we call an Earthwatch mission in ESA speak. What that means is, and the Climate Change Initiative is one too actually, these are optional programs. So that means we have to, put a proposal forward to our member states, but in the Earthwatch part, it was very much driven by the UK. It's a mission that will look at sort of establishing a very precise, very traceable space-based climate and calibration observing system. So it will be sort of the calibration mission for other missions, if you see what I mean. And the reason why it does it is because it sort of measures very precisely the sort of incoming solar radiation, the outgoing reflected radiation, with an accuracy that we haven't seen before. And this is important to understand, to estimate, let's say, uncertainties or imbalances in radiation that we haven't quite 100% understood. So it will help us to understand sort of the energy cycle impact on climate. It's not flying yet. It's being developed as we speak. I think we are in the midst of looking at the feasibility. So can we actually build such a technology, and will it be space-proof, and will it actually deliver what we want it to deliver? So that's where we are with this particular one. It's a UK-led mission, I would say. One of the novel onboard calibration system was sort of proposed by the National Physics Laboratory in the UK, near London. So, yeah.
Oh, that's interesting. I might go pop over there for a visit. So I'm really interested in the Copernicus high priority candidate missions. There are currently 6 of them listed on your website. The CO2M, Crystal, and Roselle stood out to me based on the urgency of their results to develop a solution for humankind on Earth. Can you please explain what each of those missions are designed to achieve, and how will that transcend into industry practice and or policy?
So I believe that the Roselle mission is another synthetic aperture radar mission, which will provide slightly higher resolution to the current Sentinel-1 mission, and enable better mapping with more higher revisit times for sort of crucial areas. So for instance, areas at risk of landslips, and to improve the mapping of biomass in tropical areas, to better quantify the amount of carbon stored. The Crystal mission, this is an Arctic mission, isn't it, Suzanne?
Mm-hmm.
For better quantification of sea ice. So particularly in Antarctica, sea ice is very difficult to measure. So the aim is to really improve that so that we have a better understanding of what's happening, because the volume of sea ice is a particularly important measurement, and we don't currently have those measurements from space. Suzanne, do you want to carry on with the other ones? This LSTM is an amazing high resolution mapping of land surface temperature. So that will have an amazing number of applications for agriculture, to look at heat stress for vegetation, and it will also be useful for urban areas, looking at heat islands. So I think the resolution goes down to 50 meters for LSTM. So really incredible.
And then CO2M and Crystal. What was the purpose of those missions?
One is to look at the fleet of these 6 missions, but maybe it's interesting to know why we eventually pursuing these 6 mission technology in some way.
Why are you pursuing these missions?
I think there's still different rationales here. One is that we want to basically understand our level of emissions. That was one of the main drivers. So I think the sort of priority mission probably is going to be CO2M. It's a mission that will measure our CO2 emissions globally at a very high accuracy and a sort of footprint of 2 to 2 kilometers. So that's quite a new thing to do. And then the other thing that was very high up on the priorities of what we wanted to have better observed from space was the Arctic as well, which came, for Europe obviously. It's Sentinel missions are a European endeavor. So in this one, like Sophie already said, we have the Crystal mission, which looks at sea ice thickness actually, and also snow on the sea ice, floating sea ice. And then the other mission that looks into the sort of more Arctic applications, because there's obviously the threat that the Arctic will at some point be ice-free. So that opens totally different, also economic discussions there. So SIMA, the other one is the Copernicus Imaging Microwave Radiometer, SIMA. SIMA has is mainly an ocean mission. It looks at sea ice concentration, so not thickness but concentration. It looks at sea surface temperature, very important, and it looks at salinity. So it will, to a certain extent, sort of go on from the measurements that we have from SMOS.
How will this work with the candidates? What are they required to do on these missions?
These are the 6 mission concepts, let's say, that we are currently pursuing and developing and testing in terms of feasibility. And so they will fly, let's say, CO2M, for example, will fly in 2025 only. And CO2M, for example, will help us to understand our emission levels, but for what we call the first global stocktake. So under the Paris Agreement, all the countries are actually required to quantify their emissions at a particular point, and that is in 2023 is the first one, and 2028 is the second one. So CO2M will not probably help for the first one, but should deliver data for the second one, because at the moment countries are reporting their emissions based on sort of bottom-up measurements. So they know what type of industry they have, and then there's ways of calculating what the emissions would be that a particular plant or company would, for example, emit. So that's sort of called bottom-up. But what we would like to do is we want to sort of use it also as a global snapshot, that we can sort of basically measure these emissions from space. And we can already measure some of the emissions from space, because there are other satellites that are already flying, like OCO and GOSAT from NASA. Sentinel-5P measures methane, which is another very important greenhouse gas, and has something to do with, for example, meat production and agriculture. So there are already measurements, but I think with the CO2M mission, we will have a more precise measurement of these emissions.
That's really interesting. I really believe that's something very pressing and important as well for us to act upon. It's something that I'm really passionate about, and I was thinking about. I don't think I can do this on my own, and I think I spoke to your colleague Erica when I came up with the idea that week to invent a satellite that would not only measure CO2 emissions from space, but also clean it up somehow. I would love to see something like that being invented. So the current satellite missions are building a long-term archive of essential data for local and international policy and planning. What policies are we expected to see implemented in the near future?
Yeah, that's an interesting question in some way, because I think that the closer we are coming to the global stocktake from the Paris Agreement, the more we will have to implement hands-on policies to address these limits that we've set ourselves, so to say. You know?
Yeah.
And I think just before Christmas, maybe Sophie knows more about this, but just before Christmas, I think the UK was announcing this 10-step plan for reducing emissions, I think. And, you know, you will find this in any country, really. So, you know, many countries have their own climate action plans. I mean, probably not the right word, but, you know, so basically highlighting what they're planning to do in terms of changing their, let's say, industrial setup in a country, or their energy production, for example, or their land use, to basically say, okay, we need to address, you know, hands-on how we can actually limit our emissions. So one big policy that we've seen recently is, of course, the European Union's the Green Deal. Mm-hmm. The Green Deal is not necessarily a sort of climate change reduction or mitigation program. It's more how to address it on an economic level. And that's also important, you know, how can we more adapt to what is coming our way, and how do we convert our knowledge about increasing temperatures, for example, or, you know, all the knock-on effects of this, you know, because it's not just getting warmer. I think the actual thing about climate change is, what does this global warming do? You know, for example, sea level rise or other effects, you know, that's the actual thing that we need to address. So with those, you know, global policies, I think we're setting, in Europe at least, we're setting, you know, a certain framework in which all the individual countries will have to react as well. So I think, you know, as we are coming, you know, more towards the first checkpoint, the global stocktake, I think countries will have to be more to the point in what they're going to do. One thing that we will see this year, actually, it's an event that will take place in November in Glasgow. It's called the Conference of the Parties, and this is a sort of annual event. The parties being the countries that signed up for the Paris Agreement and the UN Framework Convention for Climate Change, and they're meeting sort of once a year. They didn't meet last year because of COVID, obviously, but this year they're going to hopefully meet in Glasgow.
With masks on, or with
let's see. And you know, the major point about this meeting was that at that point, all the different countries needed to come back to say, okay, I don't know, over the last 5 years, we have said that these are our nationally determined contributions. That's what we want to do. So how are we doing, you know, against that own mark that we set ourselves? So we will probably see, you know, a adjustment of these NDCs from different countries, simply because they might simply see that, you know, what they have promised to do by now had not have the effect that they had wished for, so they need to adjust it.
No, that's great. No, that's a really great initiative, and I'm excited to see what happens as a result of that event. So one thing that really concerns me, and I'm sure the sustainable community and climate change advocates around the world, is the fact that over the years the Earth has experienced the impacts of climate change in many ways, but humanity struggles to understand the urgency until we are primarily and directly impacted by it, such as COVID. And a lot of people are reluctant to believe that climate change is even real. So with all of the evidence gathered from EO satellites thus far, how has it transformed the attitude towards this debate, and what significant action has been implemented because of it?
I don't know how it changed the attitude. I have no measurement for that one. But from my point of view, I think that the more we come up with trustworthy uncertainty characterized validated measurements, as we do in the Climate Change Initiative, the more we have a sort of physical base to say, look, it is changing and this is what we're measuring. And that might have been even different 10 years ago, when I think we didn't have such a systematic addressing of our essential climate variables, which are an indicator for climate change. Meanwhile, especially over the last 10 years, ESA has implemented the Climate Change Initiative. The Commission has implemented the Copernicus Climate Change Service, which this is sort of the operational branch of quantifying these climate indicators, and also an organization called EUMETSAT, European Meteorological Satellite Organization, has put in place a sort of similar program to the Climate Change Initiative, more looking at different ECVs simply because they have different measurements in their own repertoire of satellites. But so we now, after 10 years, actually have long-term series of these variables, and that will have made a change from, I think, 10 years ago to now. And there's also a body called the Intergovernmental Panel for Climate Change, Ipcc, which is the sort of scientific arm of the UN's Framework Convention for Climate Change. And they're coming up every number of years with an assessment report about the state of the climate. And I think they have now started to pick up the publications and results that come out of ESA's Climate Change Initiative, EUMETSAT's Essential Climate Variables, the Copernicus Climate Change Service. So the database and physical evidence is so much better than it was 10 years ago. And I think that will probably also have changed the attitude of people to recognize that the climate is changing. And maybe especially some of the extreme events, like floods, for example, are becoming more likely with a changing climate. Others not, but these ones, yes. And in these assessment reports, they say they give it a sort of probability. They say it's likely, it's highly likely, it's not proven. So basically, it gives you a confidence level of what is actually due to climate change. And I think that is something that probably people appreciate. I mean, I'm not implying that anybody's reading the assessment report from page 1 to page 1000. Absolutely not. But there are briefings, there are short versions of that for policymakers and for the general public, essentially. So that I think will change. But if you're a climate denier, I was once asked in an interview for my job. What would you say to Mr. Trump in terms of climate change if you were a journalist? And at some point you just have to say, look, I can present you the evidence, but if your mindset is different, there's nothing I can do. So, but I think people are actually realizing it. I mean, even things like.
Every single year, I feel that our summers are getting hotter and hotter, and I've noticed the impact on my skin. So I'd love to know how much you believe the sun affects climate.
Yeah, that's a whole new topic. There's the discussion about the sun cycles affecting climate change. I don't think it's any solar effect as such. Okay, we have sun cycles, 11-year sun cycles that are sometimes stronger, sometimes less strong. But I think the hotter summers are not necessarily due to that. There's a whole raft of articles, actually also put forward by C3S, the Copernicus Climate Change Service, last year as part of their State of the Climate at the end of the year.
I've just noticed the effects on me personally, and I wondered maybe if there was a link. Okay, so finally, I would love to know why you wanted to work in the space industry and why each of your roles are important to these EO missions.
That's a very good question. So I mean, from being a child, I didn't have like a sort of long-term dream of working in the space agency at all, but I mean, watching missions launch into space, sometimes they're televised, and you can see them now on YouTube whenever you want to. I mean, it's very inspiring. And I actually studied astronomy for my degree, so yeah, I kind of had my eye on space, really, but looking outwards. But during the course of my PhD, working in space physics, I kind of felt actually the impacts that we're getting on the Earth. You know, Earth is such a precious place. It's, you know, one of its kind, possibly in the whole universe, where life has developed to the extent that it has, the complexity that it has, and we won't. I don't think we'll be able to like blast off to another planet to save humanity if we mess up this one. So I really feel that to have like a role that's really worthwhile was really important to me for trying to preserve what we have here. So that's why I really love working in climate science and working in the ESA Climate Office, because I feel that it's so important that we take action and monitor what's going on, so that people have a better idea of how urgent it is.
That's so beautiful. And what about you, Susan?
Well, it was probably similarly to Sophie. It wasn't that I woke up when I was 5 and thought I'm going to join the European Space Agency.
Well, you sound very efficient, so I'm expecting a really cool answer from you, like a really good, solid plan.
No, I didn't have that solid plan. Actually, I got into space in a almost coincidental way, I have to admit. After I finished my PhD and my postdoc here in the UK, I then decided that I wasn't a pure academic person.
What was your PhD then?
My PhD was in atmospheric physics, and I was basically predicting sort of short-term rainfall over the Swiss Alps with the radar data, so not even with space data as such. And then I came to the UK and I did a postdoc by which I put these forecasted rain cells into a hydrological model to predict floods, essentially. And then when I'd done that for a year, I thought, okay, I think I need to do what I'm best at, and I decided to go out of academia and maybe more use my knowledge of science in managing it. And so I joined something that is called the Natural Environment Research Council, NERC, which at the time was part of the British National Space Centre, so what is now UK Space essentially. And I suddenly happened to be the UK's delegate to the European Space Agency, so I would go to these meetings in ESA, listening to all these satellites, etc., and found it totally fascinating, I must admit. But you know, it opened a whole new world for me. And then, you know, after 5-6 years that I'd done it, I sort of thought it's time for change, and I thought it would be so cool to work for the European Space Agency. So I started to apply for a job, and I got it eventually, and I became a mission manager, which is a title that still amuses me sometimes because I think it comes with pointy ears or something. But it was great. You know, I learned so much in being in this job as a mission manager for SMOS and Sentinel-3 about space and how you can use these data. And actually, it gave me a good background knowledge of how we measure things and what you can actually do, and the whole sort of technical side of it. And you know, after a couple of years of doing this, I again thought I would like to do something that challenges me a little bit more. And then this job came up, and I think, you know, what really attracts me on this one is, you know, climate change is the topic at the moment, I find, and to be in something that is also, you know, it's technical, but it's also quite political in some way. And if you know, you're actually really shaping something that happens every day, if you come up with the right measurements and the right information. And that I find interesting. You know, it's not something that is sort of coming in 100 years' time, and you know, it's now.
I can see you in government. I think you'd be great.
Well, maybe I'm not diplomatic enough for that one, but yeah, it's sort of the thing is, it's just, you know, it sort of interests me. You know, when something makes you go into the office with joy. Well, not at the moment in the office, but in my virtual office with joy every morning. Yeah. So that's something where I think that's interesting for me. Yeah,
that's amazing. I love both of your stories. And just to wrap up, I would love for you to demonstrate the climate app, so then my viewers get to also log on to it and see what it's all about.
But yeah, so if you go to the website cfs.climate.esa.int. CFS for sugar. Yeah, okay. Climate from space. .climate.esa.int.
Perfect.
So can you see a globe? Yes, great, perfect. Hooray.
Yay!
So this is your portal to exploring climate with data layers that can be sort of laid over the globe.
So as I'm moving the globe, all sorts of captions appear.
Exactly. So these are little pins that show the story. So we've got some stories. You can look at it two ways. There's a stories mode, which is through those little pins, and there's also a data layers mode. Exactly. Perfect. So you've got the biodiversity story there, I think.
Yeah. So I
perfect. So you
pops up.
Exactly. So you can click the panels through, and it basically So there's a little arrow there, and that shows you like the impacts of wildfires. That's telling the story of how climate is making wildfires more common, climate change, and that's affecting biodiversity around the globe.
Well, this is so interesting.
So you can click through the panels in that story, and you can also look at some different stories. There's another story, for instance, on
breaking the ice.
The breakup of the sea ice in the Arctic. So that's basically making new routes between Europe and Asia that are available across the sea. Yes. So the ice is thinning, and now you could even book a cruise liner to go through those passageways. So the amount, if you wanted to. So we're kind of talking about the possibilities that, I mean, what's that going to mean? I mean, there's going to be tourists, the pollution, the soot from the ships. Maybe that soot will settle on the ice and mean that the ice is darker, so it absorbs more energy from the sun, and then that might increase the melt happening in the Arctic. Or it could basically clouds form around little soot particles, so it could make the region more cloudy, so it could have a cooling effect. So there's lots of different processes going on with the changing activity in the Arctic that's going to be happening, and so this story just sort of takes you through what's happening, and you can see imagery from space, from our satellites, as well as at ground level as well. And then if you want to look at the data layers, could you want to have a little look at the data layers too? Because they're really great too. So can you go back to your little screen with the globe?
Yeah.
And then there's a little, the second icon along, which looks like two little sheets of paper on top of each other. Yes, so can you click on there?
Mm-hmm.
Yes, perfect. And that shows you all the different climate variables that we were talking about, the essential climate variables.
Biomass, carbon dioxide, aerosols.
Yes, that have been compiled. So for instance, you can click on biomass, and that should show you the above ground biomass stored in vegetation around the world. You can see like very dark green for high amounts per hectare in the tropical regions.
Well, I've got this.
Oh, and you've done comparison mode, so that's where you can compare two data sets and explore them together. You can look at them in as 3D globes, or you can.
So this data is made available to the public to have a look through, to analyse as well through this app. This is great. This is amazing. I can do all my research from the comfort of my bed on this app. This is amazing. And it's cfs.climate.esa.int for anyone who's watching or listening and wants to check out this app. It's so useful. It's great. It's amazing. This is exactly what we need everyone to have a look at. I'd love to see one day or very soon news broadcasters working with the space agencies, especially Earth Observation and Climate Office, to report this data regularly. I think that would be great to bring that into the consciousness of the public, for us to be aware of how important it is and what each one of us could do to help manage that better to ensure the survival of our species. You know, I think that would be interesting. And Susan, you have the powers, and you guys do as well from the office. So if that's something you can recommend to them, I would be forever grateful. And I'm sure our children, if I ever have any, would be grateful too. So thank you so much. I'm just going to wrap it up. It's been an absolute pleasure having you both on here for this interview. It's been very meaningful, especially to me, because I'm so passionate about this topic. And yeah, thank you so much.
Well, thank you for taking the time to talk to us. It was very good. Thank you.
Yes, thank you. It's very interesting. Thanks, Sarah.